Howdy everyone, and welcome back. And today we're going to talk about Gauss's law. And we've been talking about electric fields for a little bit. What's there more to learn at this point? Well, Gauss's law is going to help us calculate electric fields with more complex arrangements of charges, although we still need a bit of symmetry, but it's going to give us a lot of insight about how electric fields work. So to get to Gauss's law, we first need to understand electric flux first. So electric flux is the measurement of the amount of electric field passing through a surface. So flux is a general concept. So say we want to understand the amount of water passing through a pipe, well, we might make a mathematical surface or some type of measurement thing and track how much water is passing through just a cross section of it. So that's sort of what we're getting at. We're looking at an area, how much electric field is passing through it. So what matters here is the effective area. So I have my hand here, it has some type of surface area, and you can imagine I have a light being cast by something. The electric flux would be the size of the shadow cast on, say, a wall here. So if I take my hand and I turn it, notice how that effective area or the size of that shadow would actually decrease. So when we're talking about flux, we need both an area and sort of an angle. So we're talking about measuring electric flux, we're talking about through mathematical surfaces, not necessarily real ones. So if we're taking some charges and surrounded by a surface, this is a mathematical object, doesn't really exist, but we're using it to try to understand what's inside. Okay, so now let's take a look at Gauss's law. So we have a charge here, it's emitting electric field lines out, and we're surrounding this charge with a mathematical surface, a Gaussian surface, and that is these blue dashed lines here. We want to figure out how much electric flux there is, how much electric field is coming out of there. So we can write down the electric flux as this large phi. So the full scary calculus definition is here, but what we're effectively doing is taking this large complicated surface and turning a bunch of little surfaces and asking what's the electric field going through that little surface. So effectively we're taking all these little areas, multiplying the electric field is going through, plus some type of angle. And so how angle comes in here is with this cosine, and the angle is between the normal of the surface, so that's the angle that points directly off a surface. Say I have a flat surface with my hand. The normal vector is this thing that points perpendicular to each side. It points straight out from the surface like the normal force that hopefully we're familiar with. And this phi is the angle between that and the electric field that's passing through it. So the combination of these two terms are the effective area. It's like, again, if I take my hand and turn it, the effective area decreases. That's what this cosine is controlling. And so the total electric flux is when we take all of those surfaces that an electric field is passing through them and add them together. And so the profound thing here is that this is going to equal the charge enclosed by this surface times some constant. So this is assuming we're taking some amount of charge and completely encapsulating it with this Gaussian surface. And so this epsilon naught is just a constant of nature. It actually has to do with the strength of the electric field. We sort of hit it inside the Coombs constant. But the fact that these two things equal is a pretty profound statement. It's saying that if we take a surface and we see that there are more electric field lines coming out than in, there has to be charge inside of it. And more electric field lines means there's got to be more charge inside. Okay, maybe this is interesting, but why should we care about this? This seems like a weird concept that sure it's true, but what's the point of it? So it helps us easily find the electric field from sources that have some sort of symmetry. And so these sources, some of them could be complicated, like an infinitely long line charge or an infinite surface charge. Or we can even actually, we'll show in a minute, that we can derive Coombs' law using this. But we can take this hard, complicated problem and solve it easily in a few steps. Okay, so then let's show that. Let's use Gauss's law to derive Coombs' law. So we have a single charge here. It's emitting out electric field lines in every direction. And we're going to surround it by a spherical Gaussian surface. So this is going to do something pretty special. So remember we had that cosine phi angle. Well, it turns out if we take a surface that's perpendicular to the electric field lines always going out, then the normal vector and the electric field lines always match up. So then we get cosine of 0, and that's equal to 1. We get that everywhere. So all we're left is with the electric field and the total surface area. And you can see how this is really going to help us solve this quickly. All we need to do now, after Gauss's law tells us that's equal to the charge enclosed over this constant, is then solve for the electric field. And so what we can do is move the surface area of this Gaussian surface that we made, move it over to the other side. We've done that here. And we can ask, what's the surface area of a sphere? Well, that's 4 pi r squared. And we can notice that that actually helps us directly solve for Coombs' law, because it turns out this Coombs constant we've been assuming for a while is equal to 1 over 4 pi epsilon naught. We've been sort of hiding it inside of that for a bit. But there it is. Coulomb's law given back from Gauss's law. So we could do this for other things, like if we had an infinite line charge, we can surround it by an infinite column, and that would tell us that instead of 1 over r squared, we would get a different power law for a line charge. Or we can do an infinite surface of charge, so then we could do Gauss's law of a little pillbox, and we can find the electric field created from that. Okay, let's do another problem. So here we have a little column or little cylinder, and it has electric field lines passing through the top and through the bottom. Nothing really going on the side, so we don't have to care about them there. And so we are told the surface area of both the top and the bottom, it's 2 meters squared. We're told the magnitude of the electric field passing through. We want to use Gauss's law to inform us about what is the charge enclosed in here. Is there any charge inside here? If so, how much? So we can write down Gauss's law. We're going to write down the sum version. So we're going to know that we will need to add up the electric field along all the surfaces. And so really the only two surfaces that are going to matter here are going to be the top and the bottom. And so we know the electric field going through the top and the bottom because the electric field is just a constant through here. All we need to do is add up these two together. And you can notice how we're using a sign here. So the bottom and the top are not the same side. Well, we use a positive sign for flux when the electric field is going out from the surface, as opposed to here where it's pointing into the surface. So here, that's where this negative sign comes in. And so it's the same area, it's the same electric field, these are the same terms here, so they have to go to 0. When we subtract them, it's 0. So this is implying directly that the charge enclosed is 0. There's no charge enclosed because if there was any charge, there would be extra lines. There would be more lines going out than going in. And if there was a negative charge, there would be more lines pointing in than be pointing out. So it's saying if we have no charge in, we could track every single field line and find that it goes in and then out. There's no extra ones. Okay, we're going to do a third problem. I know it's crazy throwing in extra content. Wow. Okay, here we have a single charge living inside a hollow spherical shell. Let's have some type of thickness, but what we're interested in here is finding the electric field at all three of these regions. So there's a region here where there's just air and this charge. There's a region here where we have a perfect conductor, we have a metal, and out here where outside we have just a vacuum or something like that, or maybe just air. It doesn't really matter here. So there's gonna be 3 distinct regions. We're gonna have to find the electric field at each one of these regions. Like we just did, we know that we have spherical symmetry here. We surround our charge by a spherical Gaussian surface. We'll be able to do that in all 3 of these parts and easily solve for the electric field. So here we do that. We have the electric field and the area there, and it's equal to the charge enclosed over epsilon naught. So the charge enclosed here is just this one single charge of Q. We go and solve for the electric field. We find that we just get Coombs' law back inside, and that makes sense. There's nothing weird going on inside here. And so then we look at the second region inside this metal, and it's going to be a little different. We keep track a little bit what's going on. So we can do the same sort of thing, but here we have to ask, what's the charge enclosed? So something to know about metals is that charge is able to easily move around inside of it. I mean, that's why we use it to deliver power to our house through all these cables, all these metal cables. So metals tend to move charges that eliminate any electric field inside them. So charges tend to live only on the surfaces on the outside of metals, not really so much on the insides. So what's going on here is that the metal is going to be arranging a bunch of extra electrical charges in here, and to make it so that there's no electric field, it has to exactly move the charge of negative Q onto the surface. So we're going to find if we encapsulate a Gaussian surface here that's covering this inner part and this charge Q, Q plus negative Q is going to be 0. We're going to find the electric field inside here is going to be 0. Okay, so one last bit. We are out here in this region 3. We now want to again use Gauss's law to find the electric field. We need to use a Gaussian surface, a spherical one, and ask how much charge is in there. What's the charge enclosed? Well, we have a charge Q here. We have charge negative Q here, and since this metal is electrically neutral, it had to have gotten that negative Q charge from somewhere, and it turns out it got it on the outer surface. So although we have a negative Q here, we have to have a positive Q total on the outer surface. So we go ask, well, how much charge enclosed? Well, there's nothing on the metal total. It total adds to 0, but we still have this one electrical charge in here. So the charge enclosed here is still going to just be Q. So we're going to get back the same Gauss's law as we got in part 1. And so this is almost like there's nothing there except in region 2, there's no electric field. So this is going to be a little different. Maybe we're told that there's an excess amount of charge here, and you can see how that's going to be a little different, that the inner surface is going to negate whatever we have inside, but if, say, there's an excess charge out here, it's going to be whatever's in the inside plus that excess charge. So we'll find maybe we'll get a different answer outside than inside, but that depends on the individual problem. Okay, that's all the time I have. There's more to talk about Gauss's law, but that's probably good enough for now. Thanks for watching. Really appreciate it. Okay, thanks. Bye.